Welcome to Chapter 4 again in Payment Management System class, and today we will be continuing on Chapter 4. We talked last time about payment performance in terms of the functional performance, and today we will be talking about the structural performance. So in this lecture we will be talking more about the structural performance, the stresses, severity, and extent. First of all, we will be talking about the surface performance. So when it comes to surface performance, we will be talking about surface distresses, which typically covered in both network and project levels. When it comes to for load deflection response, is going to be mainly for project level. So to summarize, we are having two surface performance. One is the distresses and one is the load deflection response. Typically, project level, as we talked about before, would be interested to measure more information about certain project, and that's why we will be talking about load deflection response besides the surface distresses. This information is typically, as I said, it's for project level, but also sometimes for network level PMS. And the surveys can be separate because the network level definitely will not require as much details as the project level. But in the same time, from the logistic point of view, so many agencies will tend to decide to join the two systems together. So also the very first thing before we go to the field, we need to decide on what distresses are we going to survey. And basically this is going to depend on the end use of the data. For example, if we are dealing with lots of fatigue cracking, so we will have to spend more time on measuring fatigue cracking and extent and severity, and even if there is sub-types of fatigue cracking, while there is another place that they may be dealing with thermal cracking, and therefore most of the efforts would be towards this type of distress. So typically what happens is the PMS committee have to decide which data is to be used in the decision process. Besides picking on what distress to survey, we also need to know what's the amount of extent of data that we need to collect. For example, too little data is of no use because really we can't use it to predict the future performance, but in the same time you don't want to collect too much data which is going to be overwhelming to the technicians and everybody else, and eventually it won't be used. So you need to be again somewhere in between. So first of all, we need, whenever we go to the field and measure distresses, we need to define what's the severity of each distress. So the severity basically here is what is considered critical. How can I define if this distress now is critical or not? Again, this depends on the end use of the data. Typically there are three categories has been used so far. We can say low severity, moderate severity, and high severity. Some agencies, they would just say low and high. Some other agencies, if they are dealing with very sophisticated type of distress, they may even come up with a fourth or even a fifth degree of severity. So it depends, but typically the rule of thumb is low, moderate, and high severity. So the measure of the severity would typically depends on the distress type. For example, in the case of cracking, it really depends on the width of the crack. So the availability of any associated random cracking could significantly impact the classification of the severity levels. While now the other aspect that we need to keep in mind while we are in the field and observing distresses is the extent. Because I may have a very severe fatigue crack, but that crack might be one single crack, not covering the entire section area. So in order to have a full understanding of this distress, we also have to mention and measure the extent. So the extent is simply a measure of the affected area. It really depends highly on the type of distress. Typically we try to keep it simple as possible to have a measure of the extent. Most of the time we would use feet squared or meter squared as in the area of the affected by certain distress. So let's pick here on block cracking. As you can see, this is the picture of block cracking, and the question now is, how can I define the severity level of this type of cracking? So there is low severity, moderate severity, and high severity. So let's first define how I can define the low severity. Low severity is typically with any cracks with a mean width smaller than 1/4 of an inch, or if it's sealed crack. Sometimes you would go to the field and you would look at the block cracking, and there are block cracks, but they are sealed. Even if they were wide cracks, or they are very the extent is high, but if they are sealed, we would still consider them as low severity, or the width is less than 0.25 inches. Moderate severity, when the crack width on average would be somewhere between 0.25 to 0.75 inches. Really, the trigger of the high severity cracks would be a mean width of 0.75 inches or higher. How about bleeding? Bleeding, really, here the severity would depend on the amount of excess asphalt on the surface. For example, if you look at this picture here of bleeding, you could see that we can have a low severity, which is a discolored area of pavement, moderate severity, which is an area of pavement losing texture simply because of excess asphalt, or it can be high severity, which is now become to the extreme of having a shiny surface. We can see tire marks. The aggregates now are totally covered with asphalt, and you cannot see even a small piece of the surface of the aggregate, and that's considered to be again high severity. Another example here of extent measurements would be for corner cracks and polished aggregates. Here, as you see here, those are corner cracks, and typically the way we measure the extent is by the number of corner breaks per test section. Let's say if I have certain tests and I've got a certain number of corners, so as much corner breaks as I have, the severity will keep increasing. When it comes to polished aggregates, like as you could see in this picture here, it will be measured by the square feet of affected surface area. For example, if I have a section that has 100 feet squared, and then I would go to the field and I see polished aggregate, I measure the affected area, and let's say it was 10 feet squared, so that's the extent here is 10%. So in order to have a good standardized way, if I send engineer number 1 or engineer number 2 or even technician to the field and give me the same exact values, we have to come up with a standardized methodology as well as a manual to use while you are in the field. So you will report the extent and severity and the type of distress. So the manual way of doing this is really by walking along the side of the section and observe the type of distresses and the extent and severity. So the sharp distress identification manual, which is a national project that was done in the 80s, that they came up with a manual for the long-term pavement performance project, LTPP, which is the most extensive surface distress survey manual existing until this day. So you can really use it, and it's very helpful, and it's been used by so many highway agencies so far. So this is here how it looks. You can go to the Federal Highway Administration website as mentioned here, and you can download it. This manual covers both flexible as well as rigid pavements, and it's really based on the manual survey techniques which can be conducted by a group of evaluators, and this methodology have been trained on the use of the manual. So you can send technicians, get some training courses at the beginning using this manual, and then you can send them to the field and you will have a good repeatable results. So the manual method, as you may expect, it's very extensive, and in the same time it's very expensive, and it may not be realistic for small local highway agencies. So, but the good thing in the same time, it really covers a lot of details which may not be used in an agency PMS system. So we need to keep in mind again how much data do we need to collect, not too little and not too much. The other method that we also can use besides the manual method is the windshield method. Basically here the evaluators would rate the pavement from their own car. So the car will be moving on the shoulder at a very low speed, somewhere between 4 to 10 miles per hour, and by doing so eventually we're going to cover larger areas. And also the other advantage here is the facility doesn't have to be closed, but the drawback of using this methodology, it's highly inaccurate simply because still you will not be able to grasp every single distress and what's the severity and the extent of what you see in the field. The other method, which is now more advanced compared to the previous two, is the automated method. The automated method, one of the techniques is to use imaging system. In fact, the way this was started years ago by using static images. So we would use the old style 35mm camera film, which takes pictures of the road surface at the highway speed, which is, again, it can be even up to 65 miles per hour. And the ones who did this, first of all, were Pasco Rodricon, which was in Japan, which it was pretty successful in their PMS systems. So the Pasco Rodricon, basically it's a continuous film strip which is going to be recording the pavement surface, and those photographs can be taken at night with controlled amount and angle of lighting as well. So that's good. Sometimes, and instead of doing it in the middle of the day and it's going to be affected by the amount of traffic, we can do it still at night and it would still give us the accurate results. The distress evaluation also here would require manual interpretation of the photographs though. So remember, at the end of the day you would have lots of photographs, but you need to sit down and take a look at those photographs and identify, using the manual in hand, what type of distress and the severity and extent. While the other system, the GER-PHO system, that was used extensively in France. This system was more advanced. It was some sort of continuous image of the pavement surface on still 35mm film, but the distress information were extracted from the film using specially designed display table. So instead of looking at the picture manually and trying to identify what type of distress and the extent and severity, now it was hooked up with the display table that made the identification of those distresses much easier. Going now all the way to the most advanced imaging system to survey streets is the video images. So it's basically a videotape of the road surface at high speed that can go all the way to 65-70 miles per hour. One of the famous ones under this family of video images system is the ARAN system, where it's a vehicle that's equipped of acquisition system, and also it has videotaping, and also even can measure rutting and roughness by laser beams as well. And then you would see that all this information now is being plotted already, and even the cracks, as you would see here, they are already identified. So this is simply a screenshot of the computer-based automated crack detection system. So you don't even have to sit down and try to identify. The software itself would detect the type of crack and the width and the severity. As you could see here, this is a close-up picture of one of the cracks, and based again on the difference in coloring, and this is also how it identifies the width and the extent of the crack. The other type of taking the images instead of video images now is the most advanced methodology, is the laser. So now this system would use laser images and laser beams to detect changes in depth as it crosses through the cracks. It's gonna send a full array of lasers is used across the pavement to cover all the cracks, and this way it will identify the width and the depth of most of the issues that the pavement has. So this technology was used in Sweden, and the machine was named the RST, which is Laser Road Surface Tester. This machine was able to measure crack depths as well as crack width, also the rut depth, longitudinal profile, even to the extent of the macro texture of the surface of the pavement, the cross profile, as well as measuring regular distances. So it's pretty advanced. So once we measure all the data from the field, either by videotaping or laser, we need to process the data. So when it comes to the imaging system, the static image system, the 35mm pictures typically are processed manually on a special viewing table with a very highly sensitive grid to let us have the chance to see those distresses in a very accurate way and determine the severity and extent. While when it comes to the video, is typically reviewed in the office by engineers, and notes on distresses typically are taken, and it's a bit easier. While the easiest way of dealing with data measured from the field is by looking at the laser data. The laser data are typically analyzed on a board by a computer. But both video imaging and sometimes laser imaging as well, the way it works is digitize those images and try to identify cracks based on the light intensity. Especially when it comes to video image, it would identify the type of the crack itself and the width of the crack by the difference in the light intensity. A crack will typically would have more of a black shadow under intense bright white light compared to the regular surface, which will not show any shadow. So with this, I think we complete now the idea of how can we go to the field, whether manually or by any type of imaging system, to collect the data. Now the question is, how can we evaluate the pavements using the amount of data that we collected? So the question now is, after we collect all these data, what to do with them? So typically we try to use individual indices separately to make decisions based on the individual values, or we can be more productive by having a composite performance indices that can lump sum the overall performance of the pavement together in one single number. Here's an example of an individual indices. So I may deal with lots of rutting, and therefore I can come up with a rutting individual index. And as you could see here, for example, if I have a rut depth higher than 3/4 of an inch, then we have to fix this problem by designing an overlay. Another individual index might be if I have more than 10% of the area has alligator cracking and less than 10% of the section has been patched, then I have to do base repair and local dig out just to make sure that the sub base is good and the base is good, and then we would have another patch. So moving from some individual indices to more of a robust and composite index, Ashto came up with those equations. We call them PSI equations, present serviceability index. So present serviceability index is a number that is given to the pavement to give us an indication if it's in a good or bad condition. This number can be high if it's the pavement in a good condition, and it can be low in a low condition. Typically PSI would be similar to the PCI which we talked about before, which is gonna be starting from, like, this is the time, the x-axis is the time, and the y-axis would be the performance of the pavement of PSI, and the PSI would go down. So it starts from 5, and again the failure would be defined really by the importance of the structure. it can be defined here, which is 3, or it can be defined all the way to here, which is 2. So the equation that we typically use for flexible pavements under the AASHTO recommendations is this one here. So as you could see, PSI is 5.03 minus what? Minus 1.91 times the log of 1 plus SV. What's SV? SV is the slope variance, which is again an indication of the roughness, like what we talked about in the previous lectures. And then we also we need to consider RD, which is the rod depth in inches, all the way to C plus P. C is the cracking in terms of the extent of the crack. As you can see here, it's an area square foot over 1000 square foot, as well as we need to consider P, which is patching. So any type of cracking, including fatigue cracking, thermal cracking, all the way to patching, that also has to be included in the equation. Same thing for the rigid pavement, but now the coefficients are different. And as you could see, the other difference between this equation for flexible pavement and this one for rigid is that rigid pavements do not have rutting. So we don't have rutting for rigid pavements, and that's why the only thing to be considered in the PSI equation for rigid pavements would be the slope variance, any type of cracks, as well as any type of patches. Another interesting fact here that I also need to mention, that the effect of the slope variance, if you do the math, is going to be the highest factor that contributes to the present serviceability index compared to cracking as well as rutting and patches. So again, this type of index, which is PSI, was really developed to try to relate the rating of the road by a panel. So typically we would send a panel of several members to the field with actual measurements of roughness, rutting, and surface distress, and then they would go back to the office, try to collect all those numbers together to come up with one index. So as I mentioned before, the slope variance is one of the most significant variables in both cases, while the rod depth, cracking, and patching would contribute very little to the reduction of the PSI. This is clearly shown by the low coefficient. For example, for the C plus P, the cracking plus patches will have low term. Same thing for the square value of the rod depth. So if the rod depth the rod depth is less than 1 inch, then if I square it, that would be very little, and that's why also the contribution of rutting would be very low, unless if I have a high severity rutting where the depth of the rutting is more than 1 inch, then its impact would become very significant. But at this stage, the pavement is really now considered failed, even without the consideration of any other responses. So again, keep this in mind, that once we reach a very high severity rutting, this is gonna trigger by itself a failure condition for the pavement, and it would trigger a major solution such as a thick overlay or so. So by looking at the PSI equation one more time, you would see it's highly independent on the roughness, basically the slope variance. So agencies now, they realize that they need to come up with other solutions in case they want to accurately relate other distresses and rutting and patches to the overall performance of the pavement. So some of the agencies, they would develop a relationship between PSI and the roughness alone, or define other failure limits for the surface cracking, all the way to defining the failure on only based on rutting. So here, this is an example of some of the composite indices that was based on the IRI, which is the roughness only. So this is the PSI number. As you could see here, now it's empirical equation relating the roughness only. Now shifting gears to another topic here under the same theme, is we need to identify the sample units to be surveyed. As you could imagine, going to the field, it's not really feasible or even economical to survey the entire PMS section. So we need to think of dividing the sections into sampling units, and based on those sampling units we need to pick some of them to be surveyed. Not every single sample from every section has to be surveyed, otherwise it's going to be very expensive and time demanding process. So this is here, I'm just giving you an example, and I encourage you to go to Texas website and look for the similar approach that Texas DOT use. Here, based on my previous experience with the Nevada DOT, this is the identification sample unit that they use over there. So for example, when it comes to a PMS section, the criteria here is we need to have a mile-long section on the highway. This is the section, and then the sample unit is simply 12 feet times 100 feet area within the section, and the location of that sample unit would be the same unit surveyed every single year, simply because we want to see the progression of the pavement performance over the years. So if we try now to draw a mile section, let's say this is 1 mile long, and now what we do is we would come back and say, you know what, I'm gonna take a small section which is 10 by 100, and I'm gonna keep measuring the pavement performance over the years at the same exact section to see the pavement performing over the years. And again, this would be an idea on how to sample certain sections. So the section is the overall area, which is 1 mile long, and the sampling unit would be just 1200 square feet area that need to be measured every single year to see the progression of the stresses on the surface of the pavement. This is here another example of how we measure the stresses, and eventually how are they coming up with one simple index to measure the pavement performance. For example, as you could see here, we have IRI measurements to measure the smoothness of the road, and also we have rutting, we have fatigue cracking, we have patching, we have friction, and then we are defining here certain extent, and once we define the extent, we're defining also PMS points. It's we're giving certain points for every distress and extent and severity, and eventually these numbers are going to be subtracted from one single number, from one grand number, to have an overall pavement condition index. It's not the PCI, but they have their own system, which is kind of the same, where we would go to the field, measure the distresses. Every distress with its own extent and severity will have a deduct points from a grand sum number. This is here a table that shows the pavement repair strategy determination for low volume routes. As you could see here, the way we define low volume routes is by the average daily traffic. If it's less than 400 vehicles per day, and if the pavement type is asphalt, then those are the 4 different repair strategies that we need to keep. So preventive maintenance, it can be done if the rating system is somewhere between 0 and 49. That means again the amount of distresses are very minimal. If the amount or the pavement condition number is somewhere between 50 and 399, then we have to have corrective maintenance. And then if the numbers now keep increasing for 400 to 700, this is an overlay. And if the number of the accumulated distresses over time is more than 700 points, then we have to do a reconstruction. The number that Nevada DOT use is about out of 1700 points. So we keep lump summing all the numbers until we see how bad is the road. So it's different than PCI. For example, the PCI system is as follows. PCI system goes this way. A good pavement is going to have a PCI of 100, and it's going to keep failing with time from here all the way to here until we reach failure. The failure is about at 30 or 35 as a value of PCI. The way .do is kind of the opposite, where they keep accumulating the cracks points as well as rotting points, and they do not subtract it from a grand total of 100. So it keep accumulating. Let's say I go to the field and I see some fatigue and I see some rotting and couple patches. Those are gonna, every one of those is gonna have certain amount of deduct points to accumulate, and therefore their system goes the other direction. It goes this way. If the pavement is really good, then there is no points accumulated, and therefore this point here is gonna trigger a preventive maintenance. As you can see now, the numbers is only from 0 to 49. Now once I start to see the pavement is failing, that means the numbers are gonna keep accumulating until I reach all the way up here, where this is really connected to the reconstruction, where I have more than 700 points. The maximum that I have seen before was about 1700 as the maximum number of that rating system. So after we talked about the local rating system used by Nevada DOT, now let's move on to more of a national software that was developed by the U.S. Army Corps of Engineers that is used across the United States. This software is named as MicroPaver, which is basically it's a huge database management software developed, as I mentioned, U.S. Corps of Engineers, and it's really making use of the ASTM standards, both of them. The first one is D6433, which is the standard practice for roads and parking lots pavement condition index surveys, as well as D5340, which is the standard practice for airport pavement condition index surveys. So as you could tell from here, this software is really very robust software to measure and predict the future performance of both pavements on regular streets and highways all the way to airports. So this software has the capability to assist any organization and PMS management. Also, it has capability of storing construction and maintenance history, all the way to analyzing and interacting with different pavement condition records, trying to come up with a prediction in the future. That would be the ultimate goal for any software that deals with a PMS system. So as you could see, we typically measure the data and then we need to include it in the software. The software has a huge library of accepting so many types of distresses. As you could see here, those are distresses that they are identified by the LTPP distress manual, and every distress that you would include, it's gonna ask you for the extent and severity. Once you enter the extent and severity for all the observed distresses, then it's gonna be able to measure the PCI, the pavement condition index, which is out of 100. So after the MicroPaver would do the analysis, it's typically again use the condition survey information to calculate the pavement condition index. And as I mentioned so many times before, the PCI is start from 100, which is a very good pavement, all the way to 0. So once you collect the data, which is individual distresses, it's gonna come up with an overall pavement condition index. and afterwards, after we analyze the observed data and come up with a good estimate of the PCI, if you keep measuring the PCI for the same section for several years, then this is a software to be used to predict the future performance of the pavement afterwards. When it comes to the sampling units that need to be taken care of to be measured by the paver system approach, for flexible pavements, the section has to be about 2,500 square feet plus or minus 1,000, and when it comes to airports, it has to be a bit higher, which is around 5,000 square feet plus or minus 2,000. When it comes to sampling rigid pavements and the airports, there are two cases here to define for us the amount of sampling units that we need to consider. For if the slab length equal or shorter than 25 feet, then we have to measure the stresses on 20 plus or minus 8 slabs. If the slab is longer than 25 feet, then we need to come up with imaginary joints, and then as previous criteria should be assumed again. One thing here that I need to mention, that not all sample units are required to be the same size. Sometimes you are forced to have a section or a sample unit much less area than what's required. So that's okay in case you feel this sample unit would represent a totally different section with totally different pavement performance. When it comes to the network level inspection, we need to know how many sample units we need to consider. So here we're going to define two parameters, the capital N versus small n. Capital N is going to have a representation of the entire number of sample units in certain section, and maximum number of sample units we need to consider in any section is 200, while the small n is the number of sample units to be inspected. So let's say every 200 units, how many small n, which is how many small units to be inspected. So n is increased by 1 for every increase of 5 units in n, the capital N. So looking here at this table, as you could see, when it comes to the network level inspection, now we can relate the big N with the small n. This is the number of units to be inspected. If the big N is 1 to 5, then I need to measure 1 out of each 5. If n, so the capital N, is 6 to 10, then the number of units to be inspected are 2. If I have over 40 but less than 200, then I need to measure 10% of the entire area. So the other question that comes up here is, okay, I got to know what's the number of sample units that I need to inspect out of the total sample units. Also, we need to keep in mind that the selected sample unit should be representative of the overall condition of the section. For example, if I have a section that has 200 units and the majority, let's say 75% have fatigue cracking, I need to keep in mind that the sample units to be inspected has to cover both areas, that the area that is infected by fatigue cracking as well as the area that doesn't have any fatigue cracking. So the way to do so is, typically we would ask the technician to have a pre-walk or drive slowly over the entire section in order to be able to select the representative sampling units. And the golden rule that we always have to remember is, we may have an additional sampling units that should be inspected whenever a unique condition is existing. For example, again, if I have a full section that doesn't have any problem, but there is one little piece that is affected mainly by block cracking, for example, then we have to make sure that there will be some inspected sample units to cover this area as well. When it comes to airfield runways, typically we would like to sample and inspect somewhere between 50 to 100% of the units in the center of the runway, while for the taxiways and aprons we would like to inspect somewhere between 20 and 25% of the sampling units. Why the difference? The difference will reflect the importance of the center units of the runways compared to the taxiways. Now when it comes to the project level inspection, sometimes we would use historical existing charts and figures to know how many inspected sample units we need to consider, or we can use the following equation to relate the number of inspected units versus the total number of units available. So if we look at this equation here, we can define what's the n, small n, what's the number of sample units need to be inspected. Remember, those equations were built on the assumption that we have a maximum of 200 units every section. So if I know n, which is the number of units at that section, and I need to know e, which is the allowable error in the estimation of the section PCI, typically it's about 5. This is the allowable error. For example, if the PCI is measured equal to 60, I know it's gonna be somewhere between 55 and 65. That's the allowable error. As well as S, I need to know the S, which is the standard deviation of the PCI between the sample units and the section. Typically the standard deviation between different sample units is about 10 for hot mix asphalt, and it's about 15 for Portland semi-concrete pavements. Some may ask, how about if I have a section that has 5 or less than 5 units? If this is the case, then you need to survey all the units that you have. Another very important aspect while we are inspecting sample units is the randomness of selecting those units. So one of the ways to do so is this example here. For example, we need to define what's the sampling interval, I. The sampling interval is I, simply the total number of sample units over the number of inspected samples, and then we need to round it off to the whole smaller number. For example, let's say I have a section that have 47 sampling units, and I decided to measure 13 or inspect 13 sample units. Therefore the I, which is the sampling interval, is 3.6. What is 3.6? Is simply 47 over 13, and that's going to give me 3.6, and based on the rule that I was just mentioning, then it has to be rounded to the smaller whole number, which is equal to 3. What does this 3 number means? It really means that every third unit should be inspected. So the way to randomize this, now I'm gonna have a random selection of the first sample unit to be inspected. For example, if I is equal to 3, then the random start could be at sample 1, 2, or 3. The other units are spaced by I, for example 1, 4, 7, 10. So you see the difference now between 1 and 4 is 3, 4 and 7 is 3, and so on and so forth. With that, now we reach a stage here that we would be interested to know how micropaver measure the pavement condition index, and this is what we will be discussing in the next lecture. Thank you so much.